Welcome to YU. In the previous lectures, we saw how a race between a tortoise and a hare could be mathematically represented by a system of two linear equations. Graphing their distances from the starting point as functions of time, the tortoise starts first, traveling at a constant speed of 1/2 mile per hour. After giving the tortoise a 4-hour head start, the hare begins the race, traveling at a constant speed of 2 miles per hour. Since the hare's speed is greater than that of the tortoise, the slope of the hare's graph is greater, causing the two graphs to intersect. This intersection represents the point at which the tortoise and hare meet. We showed how this system of linear equations could be solved either by using the substitution method or the elimination method. Solving the system of equations gives us the coordinates of the intersection point, and thus the distance and time when the tortoise and hare are both at the same place at the same time. However, not all races where the tortoise and hare both travel at constant speeds would result in their meeting at one point in time. For example, let's say that instead of traveling at 1/2 mile per hour, the tortoise decides to use roller skates, which allow him to travel at the same speed as the hare. Since the two runners' speeds are the same, their graphs have the same slope, and the two lines are parallel. Since the two graphs never intersect, the tortoise and hare never meet. This system of linear equations therefore has no solution. Yet another possibility is that both the tortoise and hare start the race at the same time and travel at the same speed. Their graphs therefore coincide, reflecting the fact that the tortoise and hare both have identical distance values at every point in time during the race. Since the two graphs intersect at every point, there are an infinite number of solutions to this system of equations. So there are three possible types of solutions we may encounter when solving systems of two linear equations in two variables. The first possibility is that the two graphs cross. Their single intersection point reflects the fact that only a single solution exists which simultaneously satisfies both equations. That the two graphs cross. Their single intersection point reflects the fact that only a single solution exists which simultaneously satisfies both equations. Fact, two equations in two variables. The first system, so there are an infinite number of solutions. The two graphs intersect at every point. There are an infinite number of solutions to this system of equations. So there are three possible types of solutions we may encounter when solving systems of two linear equations in two variables. The first possibility is that the two graphs cross. Their single intersection point reflects the fact that only a single solution exists which simultaneously satisfies both equations. The second possibility is that the two equations describe distinct but parallel lines. Since these graphs have no point of intersection, no solution exists which can satisfy both equations. The solution set of this system is therefore the empty set. The third possibility is that the two lines described by the equations are the same. In this case, the two graphs intersect at every point, and the solution set contains an infinite number of solutions. These three types of systems are characterized by two attributes. The systems can be either consistent or inconsistent, and the equations in the system can be either dependent or independent. So what exactly do these terms mean? Any system of equations for which no solution exists is said to be inconsistent. And any system with one or more solutions is said to be consistent. The consistent systems we have seen may have a single solution when the equations describe different lines, or an infinite number of solutions when the equations both describe the same line. Equations which describe different lines are said to be independent, and equations which describe the same line are called dependent. So, consistent systems with independent equations have one solution. Consistent systems with dependent equations have an infinite number of solutions. And inconsistent systems have no solutions. We can quickly determine which type of solutions we should expect by writing the equations in slope-intercept form. Expect with dependent equations have an infinite number of solutions. We can quickly determine which type of solutions we should expect by writing the equations in slope-intercept form. Let's say we are given a system of two linear equations in two variables written in standard form. If we rewrite the equations in slope-intercept form, y equals mx plus b, by examining the constants m and b, which correspond to the graph's slope and y-intercept, we can tell whether the system has one solution, no solutions, or an infinite number of solutions. If m is the same in both equations, and b is different, then the lines have the same slope but different y-intercepts. In both equations, and b is different, then the lines have the same slope is different, then the lines have the same slope but different y-intercepts, so the lines are parallel. Since distinct parallel lines don't intersect, the system has no solutions, and is therefore inconsistent. On the other hand, if the equations have different values for m, then the slope is different for each equation. Regardless of the value of b, the lines cannot be parallel and must intersect somewhere at a single point. The system therefore has one solution and is consistent. And since each equation describes a different line, the equations are independent. If the equations of the system both describe the same line, then they must have the same slope and y-intercept. So when written in slope-intercept form, the equations will be identical. Therefore, the system has an infinite number of solutions. Since the system has one or more solutions, it is consistent. And since both equations describe the same line, the equations are dependent. In previous lectures, we saw how to use substitution or elimination to solve systems of two linear equations in two variables whose solution set consists of a single solution. In the next lecture, we will see how to interpret the results we get when solving systems with an infinite number of solutions or no solutions. Welcome to YU. We have seen in the last several lectures that systems of two linear equations in two variables can be visually represented by simultaneously graphing both equations. We have also seen that the solutions to these systems fall into three categories depending upon how the two lines in the graph intersect. If the lines intersect at a single point, the system has a single unique solution which corresponds to that point. A system composed of two distinct parallel lines has no solutions, since distinct parallel lines don't intersect. And a system composed of two identical lines has an infinite number of solutions, since identical lines intersect at an infinite number of points. These three types of systems are characterized by two attributes. The systems can be either consistent or inconsistent, and the equations in the system can be either dependent or independent. Systems which have no solutions are said to be inconsistent, and systems with one or more solutions are called consistent, having either one solution or an infinite number of solutions. We can distinguish between these two types of consistent systems by their equations. If the consistent system is composed of two distinct lines, the equations are independent. And if the consistent system is composed of two identical lines, the equations are dependent. In the last lecture, we saw that the type of solutions we should expect can be determined when the equations of the system are written in slope-intercept form. In this lecture, we will see how to interpret the results we get when solving the system to tell if the system has one solution, an infinite number of solutions, or no solutions. In the lectures so far, we have seen how to solve systems of equations which consist of two distinct intersecting lines. Using either the substitution or elimination method, we end up with a pair of values for x and y, which is the single unique solution for the system. The system is therefore a consistent system of independent equations. The solution set of this system contains the single-ordered pair 2, 4. Now let's see what happens when we attempt to solve a system of equations composed of two distinct parallel lines. Let's modify the equation used in the last example by changing negative x in the bottom equation to positive x, which changes that equation's graph so that the two lines are now parallel. Using the elimination method to solve this system, we first multiply the bottom equation by -1, and then add the two equations to eliminate a variable. But when we eliminate one variable, both variables are eliminated. But when we eliminate one variable, both variables are eliminated. And we get the equation 0 equals 4. A statement which can never be true, like this statement of equality between two non-equal numbers, is called a contradiction. Obtaining a contradiction when solving a system of equations tells us that the system has no solutions and is therefore inconsistent. Attempting to solve this system by the substitution method will also produce a contradiction. Solving the bottom equation for x, we get x equals 2 minus y, which can then be substituted for x in the top equation, producing an equation with only the variable y. The two y terms then cancel, leaving us with the contradiction 2 equals 6. Once again, obtaining a contradiction indicates that this system has no solutions and is therefore inconsistent. Since the system has no solutions, its solution set is the empty set. Now let's see what happens when solving a system of equations composed of two identical lines. This time, we'll make one equation a multiple of the other equation so that the two graphs are identical. Using the elimination method to solve this system, we can eliminate a variable by multiplying the bottom equation by -1/2 and then add the two equations. But when we eliminate one variable, every term is eliminated, producing the equation 0 equals 0. Obtaining an equation which always must be true, like this statement of equality between two equal numbers, indicates that the equations of the system are dependent, and the system is therefore consistent with an infinite number of solutions. Solving this system by the substitution method will also equality between two equal numbers. The substitution method will also produce a statement of equality between two equal numbers. We first solve the bottom equation for x by multiplying both sides by 1/2 and then subtracting y from both sides. We can then replace x in the top equation with the result, producing an equation with only the variable y. The two y terms then cancel, leaving us with the statement 6 equals 6. Once again, obtaining a statement of equality between two equal numbers indicates that the equations are dependent. The system, therefore, is consistent with an infinite number of solutions. Since both equations have the same solution set, the solution set of this system is identical to the solution set of either equation. Since the bottom equation is the simpler of the two, we will use it to define the solution set. Using set builder notation, we can say that the solution set is the set of all ordered pairs x, y, such that x plus y equals 6. In this lecture, we have seen how to interpret the results we get when solving a system of two linear equations in two variables. If solving the system produces a unique pair of values for x and y, we know that the system has one unique solution. If solving the system produces a contradiction, the system has no solutions. And if solving the system produces a statement which is always true, the system has an infinite number of solutions. As we have seen, any of these types of solutions can occur when using a system of equations to solve real-world problems. But any problem which can be solved using a system of equations can also be solved by creating a single equation with a single variable. In the next lecture, we will see what types of real-world problems are easier to solve by using a system of equations.